Welcome again. Once again, I'm Frank Jacobs, your lecturer, online lecturer in statistics. We are looking at chapter 8 on continuous probability distributions. First, we look at probability density functions. Unlike a discrete random variable, which we studied in chapter 7, a continuous random variable is one that can assume an uncountable number of values. We cannot list the possible values because there is an infinite number of them. Because there is an infinite number of values, the probability of each individual value is virtually zero. Point probabilities are zero. Because there is an infinite number of values, the probability of each individual value is again virtually zero. Thus, we can determine the probability of a range of values only. Example, with a discrete random variable, like tossing a die, it is meaningful to talk about the probability that x is equal to 5, say. In a continuous setting, example, with time as a random variable, the probability that the random variable of interest, say task length, takes exactly 5 minutes is infinitesimally small, hence the probability that x is equal to 5 is equal to 0. It is meaningful, however, to talk about the probability that x is less than or equal to 5. More sensibly, the probability that x is less than 5. Probability density function. A function f of x is called a probability density function over the range x greater than or equal to a and less than or equal to b if it meets the following requirements. 1. F of x is greater than or equal to 0 for all values of x defined on the interval, that is between a and b, as shown here. That is, f of x is always positive or 0, it's negative. 2. The total area under the curve, that is between a and b, is 1. As shown, the shaded area here is equal to 1. These two conditions being met speak to the probability density function. Once these conditions are met, the function is said to be a probability density function. The first one is the uniform distribution. Consider uniform probability distribution, sometimes called the rectangular probability distribution, because it is in fact a rectangle. It is described by the function f of x equals 1 over 1 divided by b minus a, where x lies between a and b, is shown. A is the upper limit, a is the lower limit, b is the upper limit. And as shown in the graph here, f of x, which is the y-axis, is equal to 1 over b minus a. That's just the height of the rectangle. That is going to be constant. And this area here is a shaded area between a and b, so the length is b minus a. The area is width times height, b minus a times 1 over b minus a, and that gives you 1. So that shows you right away that this area is equal to 1. Example, the amount of gasoline sold daily at a service station is uniformly distributed with a minimum of 2,000 gallons and a maximum of 5,000 gallons. So A is equal to 2,000, B is equal to 5,000. Find the probability that daily sales will fall between 2,500 and 3,000 gallons. Algebraically, we want to find what's the probability that x is greater than or equal to 2,500 and less than or equal to 3,000. And we look at the diagram here. It shows that this is A is equal to 2,000, B is equal to 5,000. And this point here is roughly 2,500 and here is roughly 3,000. So this is the area we're interested in. This is the area you're interested in. The area shaded in blue here. How to find this area? This is going to be the probability. This distance, the difference between 2,000, 2,500 and 3,000 is going to be 500, and the height is, where's my cursor? The height is 1 over 5,000 minus 2,000, and that is going to be shown on the other side, how we work that out. Probably the x lies between 2,500 and 3,000 is equal to 3,000 b minus a times 1 over 3,000, which is going to give you 0.1667. Right, this is 1 over b minus a is 3,000, and the width here is 3,000 minus 2,500. That gives you the width times the height. 1 over b minus b is always the height of the rectangle. That gives you the area of the blue, which is 0.1667. That's the probability of selling between 2,500 and 3,000 gallons. Thus, there is a 70% chance that between 2,500 and 3,000 gallons of gas will be sold on any given day. The amount of gasoline sold daily at the service station, again, same service station, is uniformly distributed with a minimum of 2,000 gallons and a maximum of 5,000 gallons. What is the probability that the service station will sell at least 4,000 gallons? Algebraically, you want to find what the probability that x is greater than or equal to 4,000. Greater than or equal to 4,000 would mean this is 4,000 about here. It goes to the end, so between 4,000 and 5,000. So we do our calculations accordingly. Probability x is greater than or equal to 5,000 is the width of the blue section here, which is, this is 5,000 point and this is 4,000 point, so this difference is 1,000. 5,000 minus 4,000 times 1 over b minus a, which is constant, 1 over 3,000. The result is 0.333. There is a 1 in 3 chance that the gas station will sell more than 4,000 gallons on a given day. That is, there's a 33% chance that the gas station will sell more than 4,000 gallons on any given day. The amount of gasoline sold again at the same service station is uniformly distributed with a minimum of 2,000 gallons and a maximum of 5,000 gallons, as before. What is the probability that the station will sell exactly 2,500 gallons? Algebraically, we want to find the probability that x is equal to 2,500, and you know what that is. It's calculated. Probability x is equal to 2,500. That means the width of this is 2,500 minus 2,500, because it's at the same point. Hence, the width is 0. Multiplied by the height, 1 over 3,000, which is constant, equals 0. Probability is 0. So the probability that the gas station will sell exactly 2,500, again, is 0. And we knew that before. Now we look at the normal distribution. The normal distribution is the most important of all probability distributions. The probability density function of a normal random variable is given by f of x equals to this formula, which looks a little ominous at this stage, and our distribution is shown here. You can see it's symmetric. The range is between minus infinity and plus infinity. And this is bell-shaped. It's symmetric with respect to the mean. Important things to note: the normal distribution is fully defined by two parameters: the standard deviation, sigma, shown here, and the mean, mu, shown here in red. The normal distribution is bell-shaped and symmetrical about the mean. Unlike the range of the uniform distribution, line between A and B, the normal distribution ranges from minus infinity to plus infinity. We say in math that the domain is a set of real numbers between minus infinity and plus infinity. Standard normal distribution. A normal distribution whose mean is 0 and standard deviation is 1, unity, is called a standard normal distribution. So we replace the mean with 0 and the standard deviation with 1, which gives you the formula for the standard normal distribution. The distribution has exactly the same shape. The mu is 0, is symmetrical about the mean is 0, and the standard deviation is 1. As we shall see shortly, any normal distribution can be converted to a standard normal distribution with simple algebra. This makes calculations much easier. This is the reason it's done, is to make calculations easier for you. Normal distribution. Normal distribution described by two parameters: its mean, mu, and the standard deviation, sigma. Increasing the mean shifts the curve to the right. Decreasing the mean shifts the curve to the left, because the distribution will always be symmetric with respect to the mean. Increasing the mean standard deviation, this degree of spread, flattens the mean. That is, the distribution becomes more platykurtic. Decreasing the standard deviation causes the distribution to become more peaked, more leptokurtic. Calculating normal probabilities. We can use the following function to convert any normal random variable to a standard normal random variable. Z equals x minus mu divided by sigma. That's the formula used to convert to Z values. We can use the following function to convert any normal random variable to a standard normal random variable. This is it, as we just said a while ago. And we will do an example to show what this is. The example is, the time required to build a computer is normally distributed. That is, the time required to build a computer at Abbott is normally distributed with a mean of 50 minutes and a standard deviation of 10 minutes. Mu equals 50, sigma equals 10. What is the probability that a computer is assembled in a time between 45 and 60 minutes? Algebraically speaking, we want to know what the probability that x is greater than 45 and less than 60. X lies between 45 and 60 minutes. The first thing we have to do is convert it to standard normal values. That is, z equals x minus mu over sigma. So the probability that x is greater than or equal to 45, greater than 45 and less than 60 is given by the probability we now convert into z values. 45, x minus 50, the mean, over 10, standard deviation, is less than x minus mu over sigma, which is just z.